In the last session, I have started covering the cleanliness measures required during continuous casting. Before that, I had talked about during secondary refining how cleanliness measures can help in achieving the desirable quality parameters. So, during continuous casting, as I have told, there are two basic issues. First, the reoxidation and renitrogenation has to be prevented, because liquid steel is getting transferred from the ladle to the Tundish and from Tundish to the mold. So, during this process liquid steel should not be allowed to fall freely, that means it has to be covered, so that there is no reoxidation, no renitrogenation, that is the first requirement. Next is there has to be some additional control measures like what I have talked about in secondary refining. So, here also during continuous casting there has to be some control measures in Tundish as well as in mold, continuous casting mold, for ensuring prevention of exogenous entrapments. The whole idea is we have taken lot of care for producing a good quality steel after secondary refining. So, all our efforts should not go to waste. Whatever good cleanliness level we have achieved, we have to maintain it, there should not be deterioration. Additionally, we have to see to what extent we can prevent additional exogenous entrapments for further improvement in oxide cleanliness. One is whatever improvement has taken place, there should be no deterioration, there has to be no reoxidation, no renitrogenation. Moreover, there has to be prevention of exogenous entrapment. Additional exogenous entrapment should not get entrapped or entrained in steel, liquid steel, so that the oxide cleanliness does not deteriorate. So, we have to be careful about those. I have told you that this is the layout. So, this is the ladle, then there is a Tundish, and then there is a mold, continuous casting mold. So, we have to be careful about some care we have to take in the ladle itself, because when the liquid steel is coming from ladle to Tundish, we have to be careful. Then we have to be careful in the Tundish itself, because the liquid steel stays here for quite some time, because ladle maybe 150 ton or 200 ton one ladle can contain, maybe 250 ton, maximum 300 ton. But when the ladle is emptied, the liquid steel comes down in the Tundish, ladle is emptied, this ladle will go, another ladle will come here, but the Tundish will remain. That is what the continuous casting is. There will be several ladles, one after another ladle will come, liquid steel will get poured in the Tundish. So, Tundish is very important as a buffer between the ladle and the continuous casting mold. Unlike ingot casting, where the ladle liquid steel is from the ladle, liquid steel is pouring directly into the mold, but that is only for one heat. But here continuous casting means several heats can be cast one after another without any interruption. For that we require Tundish, which is known as the buffer vessel. So, Tundish also is very important. As far as quality is important, we have to be careful. So, today I will talk of that, how important Tundish is. Then I talked about from ladle, when liquid steel is coming to the Tundish, there at the exit of ladle there is a flow control device. Okay. So, when liquid steel is allowed to come through this flow control device, argon injection is necessary, I had mentioned. So, there has to be a ladle shroud, is a refractory shroud, as well as there is argon injection to control reoxidation. That means no oxygen pickup should be there, no nitrogen pickup should be there. That means the air ingress has to be stopped to whatever extent it is possible, it has to be controlled. Similarly, from Tundish to mold, when liquid steel is coming down, there is a refractory shroud, we call it sub entry nozzle, and also argon injection has to be there here, because liquid, as I was telling, liquid steel should not be allowed to come down on its own in air. There has to be a cover, refractory cover as well as argon cover, so that there is no contact with air. So, these are very important requirements. Then I had talked about in ladle what can be done. I have mentioned that at the bottom of the ladle, when you are pouring or when you are doing a lot of secondary refining, the ladle here the bottom is closed, the exit has to be closed. So, how it is done? It is done with the help of an slide gate sand, because when you open the slide gate, this sand also comes down. So, we have to be careful. This sand is a source of exogenous entrapment again. This sand is necessary to close the exit of the ladle, but when you open the ladle, that means when you aim for free opening of ladle, that means when you remove the slide, open the slide gate, liquid steel should come out without any problem. So, for that the sand also should come out, but the sand should not be allowed to fall in the tundish. We have to take something, we have to take measure to remove, to take the sand so that it does not fall into the tundish. That is one, prevention of ingress of slide gate sand in the tundish, that is one. Next, I have told free opening of ladle. Ladle should open free, that means when you open the slide gate, there should be opening of the ladle, that means the liquid steel should come down from the slide gate exit. So, this is called free opening. There should not be any iron, what is that called, any oxygen poking. Sometimes it is required when the ladle is not opening free, you have to use a oxygen lance to open it. So, in that process what happens, the liquid steel gets oxidized. So, that is not desirable. So, it should open free, and for that only we are using slide gate. The proper quality of sand is very important here for getting free opening. So, when you are opening it free, then what happens? As I was telling you, we have to use argon shrouding. Now, the question is how much argon do we use? I had mentioned in the last session that we have to use around 100 liter per minute of argon to control total cut off of air ingress. If you use less amount of argon, say 30 liter per minute, then maybe 10 ppm of nitrogen pickup, and also there will be oxygen pickup. Nitrogen pickup means also there will be oxygen pickup, because both of these are coming from air. So, 100 liter per minute of argon is necessary to control, to reduce this pickup of nitrogen and oxygen. Another important requirement is a deep immersion of shroud from ladle to tundish. This helps again to control the pickup of oxygen and nitrogen from air. It has to be immersed quite deep into the tundish in liquid steel. Then there has to be a detection system to prevent carryover of slag. As I was telling yesterday, when liquid steel is coming down from the exit, from the exit of the ladle, towards the end of the ladle, slag tries to come in, because slag is there at the top of the liquid steel. So, when you are trying to empty the ladle of liquid steel, if you are not careful, some amount of slag might come. So, we have to be careful that this slag should not be allowed. The flow gate, either the flow gate or the slide gate should be immediately closed. So, how do you do that? For that, there has to be a detection system to prevent carryover of slag. When you do not have this detection system, then what do? You allow some amount of liquid steel in ladle at changeover. So, there will be some loss of liquid steel, because it is a good liquid steel. We have done lot of secondary refining attempts to make the liquid steel clean. So, we want the whole amount of liquid steel should come into the tundish, but we do not want slag to come into the tundish. So, prevent the slag, there has to be a detection system. If there is no detection system, then you keep some amount of liquid steel in the ladle at changeover, so that no slag finally comes to the tundish. Then I talked about the importance of refractory. What are the constituents in refractory which can cause reoxidation in liquid steel? I had mentioned that the refractory should not have source of oxygen, that means SiO2, sodium oxide, potassium oxide, iron oxide. The carbon also in the refractory as as an impurity should be as low as possible. Why? Because if you have SiO2, it will react with carbon of the refractory and will generate SiO and CO, these are gaseous constituents. Then this SiO will react with aluminum, dissolved aluminum in liquid steel, because you have killed the liquid steel with aluminum. So, some amount of some amount of elemental aluminum will remain in liquid steel always. So, this aluminum in liquid steel will react with SiO, will react with carbon monoxide and will generate alumina. So, again we have to remove this alumina then, which is not desirable. So, this alumina should not, too much of alumina should not get generated in liquid steel, because then this alumina again has to be removed from liquid steel, as I had told you earlier. So, the refractory material should be as much free as possible from SiO2, sodium oxide, potassium oxide, iron oxide and carbon. So, I have shown here, if you have high amount of impurity in the refractory, the incidence of clogging, that means incidence of jamming of the orifice, the refractory orifice will increase. So, we have to be very careful. If the carbon free material we use almost nil amount of SiO2, sodium oxide, potassium oxide, iron oxide. You are using mainly magnesia, refractory. In absence of all these elements, clogging index is very low and it is a good refractory, and there will be not much of generation of alumina, which is a source of again problem for cleanliness. So, this is again another important issue which you have to remember. Then let me show you what happens if you are not using shroud, either refractory shroud or argon shrouding. This we have measured, we have done a lot of experimentation with this for a continuous caster. If we do not use shroud or argon, then what is the level of total oxygen content? Total oxygen content, I have told you, is basically a measure of, because the dissolved oxygen is very small, maybe less than 5 ppm when you use aluminum killing, but there is some oxides in liquid steel, which is a measure of total oxygen content. Total oxygen means dissolved plus oxygen as oxide. So, if the dissolved oxygen content is less than 5 ppm, so if you have 45 ppm of total oxygen content, that means around 40 ppm of oxygen is present as oxide inclusions in steel, which is not desirable. So, where from it has come? Because we have not used shroud, we have not used argon. So, lot of oxide inclusions have formed, alumina oxides have formed. So, this will create lot of cleanliness problems. If you use shroud, just refractory shroud, this comes down from 45 ppm to around say 30 ppm or slightly less than 30 ppm. Just imagine what is the effect of shroud. What is shroud doing? It is not allowing the liquid steel to get in touch with normal air, from which oxygen pickup and nitrogen pickup will be there. On top of that, if you use argon shrouding, that means refractory shroud plus argon, as I have told you earlier. So, then your total oxygen can come down to 25 ppm. So, just imagine if you do not use this refractory shroud or argon, we have very high amount of total oxygen, that means high amount of oxide. So, it is a problem for oxide cleanliness, it is not desirable. So, we must use refractory shroud, we must use argon cover, argon shrouding to get good amount of cleanliness. Now, this side I have shown, if we have higher amount of total oxygen, the final CR means cold rolled coil, whatever final product we are producing will have lamination type of defect, which is getting generated from the alumina inclusions. If you have high amount of alumina inclusions, more and more laminations is a defect will be generated on the surface of the cold rolled coil. So, the percentage of such defect comes down when you control the total oxygen content in steel. So, from the cleanliness point of view, from the good quality point of view, we must use refractory shroud and argon to have a good quality of the product. Yesterday in the last session I had just started talking about what is Tundish, what happens in Tundish, what are the issues, how we have to be careful during casting, so that there is no exogenous entrapment from the Tundish. So, this is liquid steel coming from the ladle. So, this is a, I was talking of the refractory nozzle, this is the refractory nozzle, shroud, refractory shroud, and we must use some argon also here, so that there is no air ingress here. Now, this is the total Tundish. So, this from ladle liquid steel is coming here. We do not want liquid steel to straight away go to the exit of the Tundish. Why? We want liquid steel to remain for some time in the Tundish. What we call is a residence time. Residence time of liquid steel in the Tundish should be high, so that whatever inclusions or exogenous entrapments try to ingress in liquid steel will get adequate time to float up. So, for that we can use some flow control devices like dam and weir in the Tundish. These will allow the liquid steel to take a circuitous route. It will not straight away come from here and go into the exit of the Tundish. So, it allows the liquid steel to remain in Tundish for some time. So, this is called increasing the residence time of liquid steel in the Tundish. So, the flow control device have some role, dams and weirs. Moreover, I had mentioned the liquid steel should not be allowed to impinge directly at the bottom of the Tundish. There might be a damage to the lining of the Tundish. So, there is a charging pad at the bottom of the Tundish just beneath the entry of the liquid steel entry. So, it protects the Tundish bottom at this location from direct impact, direct impingement of liquid steel. So, this is again important, otherwise there will be erosion of liquid steel, erosion of the lining material of the Tundish. Now, just look at what is happening. One basically means there is a possibility of reoxidation because of air ingress, we have to be careful. Then again, when liquid steel is going and getting in contact with the slag, this one is the slag, at the top of the liquid steel there is slag. I have discussed what is the constituent of slag here. So, there may be a possibility of oxidation of aluminum in liquid steel by air and absorption by oxygen again if there is air ingress. So, we have to be careful, there should be no air ingress. Then at the slag liquid steel interface, there is a possibility of again reoxidation of aluminum if you have constituents like FeO, iron oxide, manganese oxide, silicon oxide in the slag. Like I have mentioned, in the ladle, slag should be basic and there should be less amount of iron oxide, manganese oxide, oxides like those, silicon oxide, so that there is no reoxidation. Here also there should be less amount of reoxidation. So, the slag, normally 2 layer of slag is used in Tundish. The slag, liquid slag which is just above the liquid steel must have more amount of CaO, the basicity should be high, SiO2, FeO, MnO should be very small, so that reoxidation is less. Whatever alumina is there in the liquid steel should get absorbed. So, for that more amount of CaO is necessary, but at the top of that insulation is also necessary, so that the liquid steel temperature should not come down during the process of casting. So, there is a two stage slag is used. Slag, the bottom slag which is just at the top of the liquid steel is basically a basic slag. On top of that we use rice husk, which is a good insulation material. This does not allow the liquid steel temperature to come down. So, we have a 2-stage slag. One, just at the top of the liquid steel we have a basic slag which is used for absorbing the alumina oxides which are forming and trying to get up and come to the top, and on top of the basic slag we have another constituent of slag which is known as rice husk. Basically it allows the liquid, is a good insulator, it allows the liquid steel temperature to not to fall beyond certain limits. Now this, at this point there is a possibility of erosion of the refractory, because this is the refractory lining at these locations. So dissolution of refractories, that means erosion of refractories should not take place. Erosion of Tundish refractories and reduction of SiO2 and FeO by aluminum, these are the possibilities are there if the refractory lining is not basic. As I have mentioned in the Ladle, the same thing is true for here also. Refractory lining should not have SiO2, should not have iron oxide, should not have other constituents which might get reduced by aluminum. Then at this point, as I was discussing, so some amount of deoxidation is possible in the refractory in the Tundish, because you have small amount of aluminum here. So whatever oxygen is there, dissolved oxygen, there is a possibility of deoxidation. So alumina, the deoxidant whatever is forming is trying to float and should get absorbed. So deoxidation reaction and inclusion removal, that means removal of deoxidant alumina is possible in the Tundish if you allow higher residence time, if you allow the liquid steel to remain in Tundish for some more time with the use of dam and wear. So the flow control devices are very important here. So these are the actions which are necessary in Tundish. Now I will indicate one by one what are the issues, whatever I have told I will just indicate them one by one. The insulating powder cover at top, I have mentioned rice husk type of material is used, prevents temperature loss and reoxidation prevention, this is the purpose. Then basic slag layer under the top cover, this basic slab layer it aids absorption of floating NMI, alumina, such type of entrapments. So basic slag has to be there. So on top of the liquid steel there is a basic slab, on top of that there is insulating powder like rice husk, but there should be less amount of carbon in the rice husk, because rice husk should be burned so that carbon goes out, otherwise there is a possibility of carbon pickup. So we have to be careful about that. Now I have mentioned about the dam and wear and the turbulence arrestor. So all these flow control devices, where do you put them? So here is a question of doing some mathematical modeling of the Tundish. Lot of people have done lot mathematical modeling to determine the location of dam, wear and the turbulence arrestor, so that you have more residence time of liquid steel in the Tundish. We have less turbulence in the Tundish, you have less amount of dead zone in the Tundish. So for this optimum location of dam, wear and turbulence arresters are necessary. Then as I was mentioning, we must have a good insulation, it should not cause contamination or temperature loss, this is very important. Then the Tundish stopper with porous plug and argon, this is very important, because this prevents contamination with clogged alumina. So as I was telling you, so like here is a flow control device from Tundish when liquid steel is allowed to come in the mold. So here you must use argon to prevent reoxidation and renitrogenation. So there is a refractory nozzle, we called it sub-entry nozzle, which comes from the Tundish bottom to the mold. So there must be some flow control device to control the liquid flow. Whenever it is required it can be stopped, whenever required it can be opened, to what extent it is open, there has to be a flow control. Along with the flow control in the refractory nozzle we must have argon injection. I have mentioned about this, why it is necessary from Ladle to Tundish. Similar way it is necessary from when the liquid steel is coming down from Tundish to mould, continuous casting mould. So, as I was mentioning, the Tundish stopper with porous plug should have provision for argon flow. This is very important. Otherwise, there will be a possibility of clogging of with alumina, because we have killed the steel with aluminium for good killing, for good deoxidation. So, there will be some small amount of aluminium in liquid steel, elemental aluminum in liquid steel, which if it gets in contact with air will form alumina, and there is a possibility of clogging. We must not allow that. So, argon shrouding, argon cover is very much important. So, what I am mentioning here is, like Ladle, we are doing a lot of efforts to bring down the total oxygen level. In Tundish also some reduction in total oxygen is possible. Total oxygen is possible means oxide inclusions, whatever are forming, whatever contamination possibilities are there, if we allow them to stay in the Tundish for some time, those inclusions will float up and get absorbed by the basic slag. So, some amount of total oxygen reduction or some amount of cleanliness improvement is also possible in Tundish. Now, after Tundish, when you are using continuous casting, there is mould, is a continuous casting mould. Whether you are doing casting of bloom or billet or slab, whatever it is, there has to be a continuous casting mould. The shape of the mould of course is different depending on what you are casting, but there has to be a mould. The mould, what is a mould? Mould is basically, unlike ingot casting, it is an open mould. You see, this is the mould surface, this is made of copper, this is water cooled copper, this is a copper mould. So, liquid steel is coming from the Tundish through this nozzle, which is we are calling it sub-entry nozzle, SEN. So, this is the port, nozzle port, through which liquid steel will come inside the mould. So, what is happening? Through this port liquid steel is coming, also we are passing argon. So, there is some argon bubble also is coming out in the liquid steel. So, this will go, we take this path, go to the surface, we have mould flux or mould, we call it mould powder. Initially we use powder which will in contact with the liquid steel, so some amount of liquid flux will form, we call it mould flux. So, this is liquid flux which is forming from the flux powder. So, this is melting, so there is some amount of liquid. So, there is some turbulence. If there is too much of turbulence, that means some amount of entrainment of liquid flux is possible. We do not want that, because what is liquid flux? It is basically some oxides, it is a calcium oxide, alumina oxide, some amount of other oxides are also there. So, we do not want that. Some sodium oxide is there, some silicon oxide is there. We do not want slag to get entrained here. So, again lot of modeling has been done just to ensure that there is not much of slag entrainment because of too much of turbulence with the liquid steel which is coming inside. So, this is very important. Now, look at here, this is that flux powder, this is the flux rim, and here you have a molten, whatever molten liquid is there in the slag will come here, will get inside, because that this is not stationary. All of you are aware that the casting mold is not stationary, it is getting movement like this. There is a vertical movement, top and down, top and bottom, it is moving. Otherwise, there is a possibility of sticking of the shell. This is the solid shell which is forming during solidification. It might get stuck. Why it does not get stuck? First, there is liquid steel here, there is a molten slag here which is preventing the shell to get in touch with the copper mold, and also there is a vertical movement of the copper mold. So, this helps the liquid rather the solid shell not to get stuck with the mold surface. This is very, very important. So, what happens because of the shrinkage, there is a possibility of formation of air gap here, because the shell liquid shell from the liquid steel, whenever solid shell is forming, solidification causes shrinkage. The volume is, there is a volume change, so there will be a shrinkage. So, there is a shrinkage means it comes down, comes away from the mold. The ferrostatic pressure of the liquid will try to push it towards the mold, but the shrinkage will try to take it away from the mold. It depends which force is more. So, some amount of shrinkage will also be there always. So, we have to be careful about this air gap. Too much of air gap formation means, what is air gap? This is insulation, it will cause insulation. So, the liquid steel we should get cooled. How does it get cooled? It gets cooled by the copper mold. Water is flowing inside the copper mold. So, this is chilled mold, water cooled mold. So, the heat transfer is there, from here heat is going out in this direction. So, if there is a air gap formation, so there is a insulation. So, there is a heat transfer gets impeded, heat transfer is less at these locations because of air gap formation. We have to be careful about that. So, after the mold, below the mold, there are supporting rolls, and in between there is a water spray. This is a primary cooling is done in the mold, but when the shell is coming out of the mold, the shell thickness has to be sufficient, all of you know, otherwise there will be a breakout. So, the strength of the shell when it is coming out of the mold, because unlike ingot mold, there is nothing at the bottom. So, the liquid steel is supported by the solid shell here. Thus, the solid shell must have adequate strength, otherwise there will be rupture of the solid shell and there will be breakout, and there will be a chaos. The whole casting has to be interrupted. The casting floor will be flooded with liquid steel. There might be accident. We have to be very, very careful about that. So, the shell thickness is very important. So, below the mold, the cooling is done by water. So, this is called primary cooling inside the mold. Below the mold, it is called secondary cooling. It is done by water or air mist. There may be a mist, means air and water combination. There may be mist cooling, there may be water cooling, it depends. Mist cooling is better because it is more uniform, more soft, which is always desirable. But there has to be, additionally there has to be some support rolls. Otherwise what is going to happen? This shell here, the thickness is not much. So, there is always a chance of this ferrostatic pressure will try to push the shell, because there is no support now. Inside the mold there was some support. When you are coming out of the mold, below the mold, there has to be some support rolls which will act as a support to the thin solid shell. Solid shell is increasing in thickness. At this height, still there is not much of solid shell. The thickness is not much, so there has to be some support. This support is given by the rolls, moving rolls. There are two purposes of the rolls. First is the support, another is it allows the shell to come down. So, that is also another purpose, because the rolls are moving this way, it is not stationary rolls. So, this gives a downward movement to the shell. So, there is air cooling and there is support rolls. So, in the mold also there is a possibility of contamination. Contamination from where? As I have told you, contamination from the mold slag which is present here. If there is too much of turbulence, there is a movement of the mold, top and bottom, we call it this movement is very much necessary, otherwise there is, as I have told you, there is a possibility of sticking, shell sticking. So, this mold also, we call it mold oscillation, it is oscillating, it is going up, going down, it is oscillating in a particular, there is a frequency how oscillation will take place, there is an amplitude to what extent it will move up and down. So, because of that or because of the turbulence, the liquid still level at the surface here should not move or move up or come down very much, because the turbulence has to be controlled. Otherwise, the turbulence is much, then there is a possibility of entrainment of the here liquid slag at these locations. There is a possibility here, here it is shown. So, the turbulence in the liquid steel within mold is very important. Turbulence should not be much, otherwise there is a possibility of contamination from the liquid slag which is at the top of the liquid steel. So, there is a possibility of entrainment of liquid slag in the mold, which is not desirable. So, we have to be careful in the mold as well. So, now let us see what are the issues in mold for getting good cleanliness. SEN is, as I have told you, sub-entry nozzle must have suitable configuration and optimum submergence. Submergence is important, like as I have told in the Tundish also there is submergence, here also there is a submergence. Otherwise, what is going to happen? If it is not, the submergence is not within, if the SEN is not submerged in liquid steel, there is a possibility of air ingress. So, there has to be some submergence. Moreover, the liquid steel is coming out from these ports. So, if there is not submergence, that there will be too much of turbulence at the top of the this is called meniscus. At the meniscus there is a problem. So, this is called sub-entry nozzle, this is submerged, this entry nozzle is submerged. So, what should be the submergence? Again, modeling can determine what should be the optimum level of submergence, what should be the orientation of these ports, whether it will be horizontal, whether it will be at downwards, whether it will be at upwards. All these have implications of the flow and turbulence of the liquid steel in the mold. So, modeling plays a big role here in deciding what should be the configuration of the port, exit port here. So, SEN of suitable configuration and optimum submergence, this is very important. This helps flotation of NMI, whatever exogenous entrapments are getting generated. Suppose liquid slag, mold slag is getting entrained in liquid steel, we must give sufficient time for them to float up. Too much of turbulence is not desirable, but some amount of turbulence will help them to float up and get absorbed. So, this is important. Then granulated casting powder with good flowability. I have told you that powder is used for lubrication in the mold, which will get molten and generate slag. But what should be the powder? It should be granulated, it is not just powder, for good flowability it is granulated casting powder, it is not just normal powder. Granules are formed from the powder. By melting we get granules, so we have good flowability, this is very important. So, this gives uniform powder coverage. You see this is a flush powder, it should be uniform, because this also determines heat transfer to certain extent. If the powder coverage is not uniform on the top of the liquid slag, somewhere it is less, somewhere it is more, then the heat transfer gets different. From one point to another there is a difference in heat transfer, which is not desirable. So, the powder characteristic is important. So, granulated casting powder with good flowability, this is very important. So, to get uniform powder coverage with less entrapment, we do not want entrapment This is the desirable requirement. Then this powder will generate the slag. Now, this slag should have optimum viscosity and surface tension. This is again important. Why this is important? First, it should not get entrained, so viscosity and surface tension, because there is an interface between liquid steel and mold slag. So, the surface tension, interfacial tension is important, the viscosity is important, so that even if there is some turbulence, this slag should not get entrained, number 1. Number 2, this slag for getting good lubrication should get inside this. That means the slag should come down. So, viscosity plays an important role here. If the viscosity is too high, slag will not come down, it will not give the desirable lubrication, and there will be a breakout. So, there will be a sticking between the shell and the mold surface, and that is not desirable, there will be a breakout. So, proper amount of viscosity is very important. So, this is given by the whatever the constituents are there. What are the constituents? Whether how much of CO, how much of alumina, how much of sodium oxide will be there, how much of barium oxide sometimes are added, how much of calcium fluoride will be added. All these will give you what is the melting point of the powder which will generate the slag, what is the viscosity, what is the surface tension. So, the constituents present in the powder will give us the desirable mold slag, which has optimum viscosity and surface tension and melting point. This is very important. Slag entrainment should not be there, and then control of mold level fluctuation, this is very important. As I have told you, because of many factors, because of the turbulence, there is a possibility of level fluctuation. This meniscus level, there is a possibility of fluctuation going up and down along with this. Along with the normal movement of the mold, there is a possibility of fluctuation, there is a possibility of additional turbulence which causes some amount of vertical movement of this surface, which is not desirable, because there is a possibility of entrainment of mold slag. So, for that there has to be a proper control on mold level fluctuation. It can be done. So, it is normally done there, mold level fluctuation. So, it prevents slag, or too much of fluctuation means even the powder which is present at the top of the slag, that might get entrapped. Small amount of fluctuation, turbulence will cause slag entrapment. Too much of fluctuation might cause even powder entrapment, which is very, very undesirable. So, mold level fluctuation control is very important. Then where from fluctuation takes place, too much of sudden change in casting speed. Suppose you are casting at a speed of say 0.8 meter per minute. Now, suddenly if the speed increases to say 1.1 meter per minute, or suddenly it decreases, there is a problem. Too much of fluctuation will take place. That is called unsteady state of casting, which is not desirable. Steady state means you are casting at a particular speed without much of fluctuation. So, such non-steady state is not desirable. Too much of change in casting speed is not desirable. Then, as I have told, argon shrouding to prevent nozzle clogging is very, very important. If you do not use argon here, there is a possibility of clogging of these ports, as it happens for from Ladle to Tundish refractory nozzle port. Here also there is a possibility of clogging. So, because there is some aluminum in steel, so if there is a possibility of ingress of air, alumina will form, this will cause clogging of this port. If the clogging is too much, maybe the casting has to be interrupted, because no liquid steel will come out from the port. So, what happens? The casting has to be aborted. So, clogging has to be controlled by whatever means available to us. So, this I have mentioned here, sudden change in casting speed is not good, argon shrouding is desirable. So, if we do all these measures, some amount of cleanliness is additional cleanliness is also possible in mold. Most of the cleanliness, as I have told you, we have taken care of in the ladle in secondary refining. Some amount of cleanliness enhancement we have done in Tundish. Then small amount of cleanliness enhancement we can do in mold also if we take a lot of care, if we do not allow any entrainment of liquid slag, we do not use, rather we use argon of desirable to the desirable flow, so that there is no air ingress. We do not use too much of change in the casting speed, too much of turbulence we do not want. So, if you take all these measures, then some amount of enhanced cleanliness is also possible in mold. So, our purpose is whatever good liquid steel we have produced in ladle after secondary refining, that should be maintained and that should be enhanced, the cleanliness level should be enhanced, that should not get contaminated. Any amount of exogenous entrapment has to be restricted. So, in mold, exogenous entrapment is the mold slag or the mold powder, this has to be controlled.